I'll start with A. Let's see, let's put these up. What should we talk about today? What do you guys talk about? On Thursday, let's see, good question. I feel like my paper on this is like I had at one like. Last, I feel like we got kind of. What did we do last Thursday? I think we talked about graphing a bit. And we talked about inverse curve functions kind of a lot because. Yeah, I remember that. That was on Tuesday. Okay, that was on Tuesday? Yeah. What did we do on Thursday? Back in the notes here. Yeah, we started talking about graphing and kind of finding relative extrema and that kind of stuff. And also concavity and inflection points. Oh, yeah. So we should probably continue in that vein. I mean, is there anything you would like to cover?
Probably concavity.
Okay.
I really like spot.
Sure. Okay. You all the folks on Zoom as well, if there are things you want to see, my plan today was to talk about kind of more graphing stuff, including concavity, second derivative, and also to probably start talking about some optimization stuff, because that's kind of the other thing we do with this. So, yeah. Just a reminder, we don't have class on Thursday, it's Thanksgiving. And then next week is the last week of classes, and then the week after that is finals. So we're rapidly approaching the end here. I'm going to use my red pens because they still have ink in them. All right, let's see here. 1 second. Not you. Not you. Maybe you. Well, I should grab one other thing. We talked about this one. So let's just say a couple things first and foremost before we get too carried away here, as far as it goes for increasing, decreasing, up, concave up, concave down. So 2 things. For a function f of x, if f prime of x is greater than 0 on some interval, then f of x is increasing on that interval. And similarly, if the first derivative is less than 0 on some interval, then the function is decreasing on that same interval. And in a similar way, it looks very blurry. Let's. No. Yeah, it looks a little better, I feel like. Let's zoom in a tiny bit here. There. Okay. Similarly, this pen's not so great either. If the second derivative is positive on some interval, then we say that the function is concave up. On that interval. And similarly, if the second derivative is negative on some interval, then we say the function is concave down. Remind everybody, concave up, like a cup. Oh, yeah, my pens. Pens are on the way. They've been ordered a while ago. They might be coming via UPS though, which could be an issue. So let's see. Concave down, like a frown. So what we're gonna do is we're basically gonna incorporate all the, and then I should say, so, and then the other thing is we have an inflection point at C comma f of C if the concavity changes from one side of that point to the other, from one side of C to the other. Yeah.
Is that last thing we come over with or don't we?
As long, I mean, that there's, so I should point out, concavity is kind of funky. It's actually, the definition here is a little bit more. Yeah, the definition is a little kind of, it's actually really interesting. So the concavity has to change and the function has to be defined, of course. And it also has to be that the function has a tangent line at that point. So it's not that the derivative has to be defined. So let me show you something. Well, let's talk, we'll do some examples and then we'll talk about kind of when you may or may not get in the function point. It's kind of weird though. So let's look at something like, what do we got here? Sure, let's look at this one. Let's look at f of x equal to x squared times the square root of 12 minus 2x squared. And the idea for all these functions going forward is we're going to graph them. And when we say we're going to graph them, we're going to include all the following: x and y intercepts, any asymptotes, so horizontal asymptotes, vertical asymptotes, maybe even a slant asymptote here and there if we have them. And then we're going to include what I like to call all the first derivative stuff. So the first derivative stuff is where the function's increasing or decreasing. We don't usually write that down, but we definitely see it from the sign chart when we find where the function is going to have relative extrema. So increasing, decreasing, and any relative extrema. And then we're going to include all the second derivative stuff, which is where it's concave up, concave down, and any possible inflection points. So typically, well, in fact, I'll just walk you through as I go here. So let's look at this. And I suppose first and foremost, before you do any of that stuff, you probably need to think about what the domain of the function is. So if we look at f of x equal to x squared times the square root of 12 minus 2x squared, this definitely has a very limited domain, right? If I think about 12 minus 2x squared being greater than or equal to 0, I have 2 times 6 minus x squared being greater than or equal to 0. It looks like I have 2 times the square root of 6 minus the x times the square root of 6 plus x being greater than or equal to 0. If I look at the number line there, I'm stuck between negative root 6 and positive root 6. Because if x is bigger than root 6, it's going to be negative. If x is between those two, it's positive. If x is over here, it's negative. So we are limited to being just from here to here. Yeah, Manny.
Is there any reason then just put, is there a reason you factor this? Don't you just put the x squared on the other side?
I could. I would say it's usually easier to solve an inequality via factoring. If I were to say, I mean, you're totally right. I could say I have 6 bigger than or equal to x squared, and then take the square root of both sides. I just have to be careful, right? Because if you take the square root of both sides, then what you're really saying is the absolute value of x is less than or equal to the square root of 6.
Yeah, which means that it's greater than negative square root of 6.
Right. But I feel like it's safer to go this way. But yes. So we've got our domain, and now we're going to find, let's see, so definitely if your domain is limited like this, there's no possible, I'm getting ahead of myself, sorry. Let's find the y-intercepts. So y-intercept, we're going to set x equal to 0. We're going to get f of 0 equal to 0. X-intercepts, we set the whole thing equal to 0. And we see that we get x equal to 0. And here we get x equal to plus or minus the square root of 6. If I find asymptotes, I don't think we're going to have any asymptotes. We can't have a horizontal asymptote because the way you get a horizontal asymptote is by taking the limit as x goes to infinity of your function. And x can't go to infinity because it's not in the domain. And because again, horizontal is really just asking what's the behavior of this function as x gets really, really, really large or really, really negatively large. And we don't have the option here. Vertical asymptotes, also not an option. Well, it's not that it's not an option, it's that this function x squared times squared 12 minus 2x squared isn't undefined anywhere. We don't have division by 0, which is usually what gives us a vertical asymptote. So, right, there's no division by 0. Technically, that's not the only way you get a vertical asymptote. You can also get a vertical asymptote if you have a logarithm, but those are kind of the only two ways.
So for vertical asymptote, does the part of the function that's undefined have to be within the domain? Not within the domain, but around the domain, because here the function is undefined before negative square root of 6 and after negative square root of 6, but we don't get a vertical asymptote.
Correct.
Is that a property of square roots or?
So it's more about the kind of way it's undefined. So typically when you're getting a vertical asymptote, it's because you've got like something like 6 over x. And really, I should say vertical asymptote, what's happening really is you have the limit as x approaches whatever your vertical asymptote is from either side of your function being some sort of infinity, right? Because the function is getting infinitely large or negatively infinitely large. And that's not what's happening here. If you plug in square root of 6, you're just getting 0. So then we move on to the first and second derivative stuff. So, question, yeah. All right, one more time. None. It says none. Sorry. You're all, nice. Yeah. And because there's no division by 0. So then we move on to the first derivative stuff. So I'm going to take my first derivative. F of x, I'm going to rewrite it as x squared times 12 minus 2x squared to the 1/2 power. I'm going to take my derivative. It's going to be product rule. 2x times 12 minus 2x squared to the 1/2 plus x squared times 1/2 times 12 minus 2x squared to the negative 1/2 times the derivative inside stuff, which is negative 4x. And I definitely want to simplify this because the whole idea here is I'm going to take my derivative and then find my critical values. And really, we have to be able to factor simplify as much as possible. So let's see, I can factor out a 2x for sure. I can also factor out a 12 minus x squared to the lesser power. Right, we're always factoring out the smaller power. I'm going to factor out 12 minus x squared to the negative 1/2.
Minus 2x squared.
Where is that missing? Oh, down here. Thank you. Yeah. Good call. So then here I'm left with a 12 minus 2x squared to the 1. And over here I'm left with I factored out a 2x, but I'm still left with a x squared and a negative 1. So I'm left with a negative x squared. No, because it's a 1/2 times negative 4 is a negative 2, and I factored out the 2. Yeah. And then we're going to set that equal to 0. I'm going to do a little more simplifying. I'm going to write this as 2x. This in here becomes 12 minus 2x squared minus x squared is 12 minus 3x squared. And I'm dividing by 12 minus 2x squared to the positive 1/2. I'm saying that equal to 0. Slash undefined. The 3x squared. So I have a 12 minus 2x squared minus x squared, and minus 2x squared minus x squared is minus 3x squared. So then, if we set this equal to 0, we can see that we're either going to get x equal to 0 from this piece, or if I set 12 minus 3x squared equal to 0, I can factor out a 3. I'm left with 4 minus x squared equal to 0, and that factors as 2 minus x times 2 plus x. So I get x equal to 2 and x equal to negative 2. And technically, I should also include plus or minus the square root of 6, because plus or minus root 6 makes the denominator equal to 0. And that is certainly a critical point, because wherever the derivative is either undefined or 0, as long as it's in the domain, which plus or minus root 6 both are, we're good to go. So here's the number line I'm going to draw. I've got my negative root 6, my root 6, Really, nothing is happening out here, right? The function is totally undefined out here. I've also got my -2, 0, and 2. Might not have left myself enough room here. That's all right, though. So then what we're going to do is we're just going to test a point in each section. Now, it's kind of terrible. It's probably to our benefit to factor this a little bit more. Here's what I mean. If I write this as 2x times 3 times 2 minus x times 2 plus x over the square root of 12 minus 2x squared, it might be a little bit easier to see what's happening when I look at what's happening in each section. So if I pick a number between 2 and root 6, I can only think of really one good option, the square root of 5. Definitely bigger than 2, definitely smaller than root 6. If I plug in root 5, let's see, maybe it would be able to go here. I don't actually know. Sometimes it's, yeah. If I go back here, even though I just thought that wasn't the place to go. Root 5 squared is 5, 3 times 5 is 15, 12 minus 15 is negative, 2 times 5 is positive, and this bottom part's always going to be positive. So positive, negative, positive, the whole thing is negative. And then at 2, we're going to change signs. At 0, we're going to change signs. At -2, we're going to change signs. You keep plugging in points, right? Like you could plug in x equal to 1 and get positive, positive, positive. You plug in x equal to -1, get negative, positive, positive. You plug in x equal to negative root 5, get negative, negative, positive. Or you can see that each factor has a power of 1. So every time you go over that factor's 0, you're going to change signs. Yeah.
I think you've said this before. I just want to make sure I got it. So generalization is if the function has an even power or even number of factors.
If the factor has an even power.
Okay, so now
All these factors that my zeros are coming from, -2, 2, and 0, all have odd powers. And since each of those zeros have odd powers, the sign changes every time we cross over them.
if it was even, the sign would be negative.
Correct. Which we'll see an example of. So here we would say our function is increasing, decreasing, increasing, decreasing. So we have a relative minimum at x equal to 0. And we have relative maxima at both x equal to 2 and x equal to -2. Questions?
So the sign chart guarantees that it's a relative maximum or a minimum, depending on the sign of the derivative.
Right. So if as long as you have a critical point where the function is defined, if your function goes from increasing to decreasing, you have a relative maximum at that point. That's what the first derivative test says. And we also typically want to find the y values because we're going to graph this thing. So if I know that I know for x equals 0, I already found the y value was y equals 0. For x equals 2, the y value is going to be f of 2, which is going to be 2 squared times the square root of 12 minus 2 times 2 squared, which is going to be 4 times the square root of 4, which is 8. And for x equal to -2, you get y equal to f of -2, which is going to equal -2 squared times the square root of 12 minus 2 times 4. Which is also going to be 8. So now here's what I'll say. We haven't even touched the second derivative stuff, and already we have plenty of information to help us graph this thing. So often I kind of ignore the second derivative stuff until after I've already graphed it. Because usually it's nice to kind of just do the graph without that information. Not always, but a lot of the time. So let's see what we've got so far, graphically. Our function, we know, has a y-intercept of 0. We've got x-intercepts at the square root of 6 and 0 and the negative square root of 6. Kind of plotted those a little bit off, that's right. And then we know we have a relative maximum at 2, 8 and at -2, 8. And relative minimum here. It's going to look something like this. And I can see that this, oops, sorry. I can see that this matches with my sign chart that I just made, right? This function is increasing from negative root 6 to 2, sorry, negative 2, decreasing from negative 2 to 0, increasing from 0 to 2, decreasing from 2 to positive root 6. Now, you can also probably see that it looks like we have some changes in concavity. It certainly appears to be concave down here, concave up here, and concave down here. So there's probably an inflection point somewhere right about there and somewhere right about there. Did you have a question?
Yes, so when we have the graph, that is not what it says. After the theorem, didn't explain it too much, but one of the theorem that he said was, if I understand it correctly, the first derivative, if the first derivative is 0 and the second derivative is positive, then it's a relative.
That theorem is called the second derivative test, which we can talk about in just a minute, actually. So there's two different ways to test if you have a relative maximum or relative minimum. One way is what we just did using the first derivative test, and which is definitely the test I would normally recommend. It's more helpful for graphing it, and it's always conclusive. There's also another test we'll talk about in a second called the second derivative test for relative extrema. That shows you if you have a relative max or relative min, but it doesn't always work. Yeah, there's a reason we would learn it. The reason is because it comes up when you talk about functions of multiple variables in 21C. It is the de facto test to see if a critical point is a relative maximum or relative minimum. So yeah, it does come back, but in this class, you wouldn't really use it most of the time. So let's talk about finding the inflection points. So here's our first derivative, which is not pretty. Our first derivative is 2x times 12 minus 3x squared over the square root of 12 minus 2x squared. And if I was going to take the derivative of this, which I'm going to do, I would probably actually make the top not factored out. I would write this as 24x minus 6x cubed over 12 minus 2x squared to the 1/2 power. That's the better starting place for me. I don't want to have to use the product rule in the top, but I don't really have to. So then my second derivative is not going to be very nice. It's going to be at the bottom times the derivative of the top, which is going to be 24 minus 18x squared minus the top. Now, if I'd been smarter about this, I would have factored out a 6 from all this one before I even got going. But I didn't. It's too late now. I mean, I can start over, but it's fine. We'll factor out a 6 in a second. And then the derivative of the bottom is going to be 1/2 times our stuff to the negative 1/2 times the derivative of the inside stuff, which is a negative 4x. All divided by the denominator squared. Oh, thank you. It's just rife with mistakes. So there's the whole thing. We're going to simplify kind of like we did before. We're going to factor out as much as we can. So I can definitely factor out a 12 minus 2x squared to the negative 1/2 from the top. So I've got a 12 minus 2x squared to the negative 1/2. I can also factor out a 6. And I think that might be it. Let's find out. So from this first piece, I have a 12 minus x squared, sorry, 12 minus 2x squared to the positive 1. And I have, if I factor out a 6 here, I'm left with a 4 minus 3x squared. Over here, if I factor out a 6, I'm left with a 4 minus x cubed. 4x, sorry. My brain just doesn't want to get all the x's for some reason. And a 1/2 times a negative 4x is a minus 2x. And the 12 minus 2x squared to the negative 1/2 got factored out. All divided by 12 minus 2x squared. We bring this down, and this actually brings up something I want to point out because it keeps on coming up, and I should say it. After I've taken this derivative and simplified, the new power in your denominator, if you're using the quotient rule, should end up being exactly 1 larger than it was before. We started off with a 12 minus 2x squared to the 1/2, and after simplifying this, we're not quite done, but we will end up with a 12 minus 2x squared to the 3. Yeah, but I wouldn't. I mean, you're not wrong to make that statement, like, it's definitely a possibility here. It's just, I don't know, we're still gonna try and set this equal to 0 and solve for critical points for the second derivative, so usually I don't use logarithm differentiation unless it actually needs to be done, or is I'm told I need to do it. Simplifying the insides here, nice. So I have to multiply this all out. I have 12 times 4, I have 12 times negative 3x squared, I have negative 2x squared times 4, and I have a negative 2x squared times 3x squared, negative 3 is positive 6x to the 4th. And then I have a plus 2x times 4x, and I have a plus 2x times negative x cubed. It's a minus 2x to the 4th. That is really gnarly looking, right? Now we're expecting to get some critical points, I don't know, somewhere like around -1 and 1 or somewhere about there, but this is kind of a lot. So simplifying this, I have a 6x to the 4th minus 2x to the 4th, so I have a 4x to the 4th. I don't have any x cubed, which is mildly surprising, but I don't. And then I have a minus 36 minus 8 plus 8, so that's a minus 36x squared. And finally, I have a 48. Am I missing anything? Okay. So then from here, I can factor out a 4. I'm left with x to the 4th minus 9x squared plus 45, 12. Geez, this problem is terrible. This is, so I will point out, this kind of problem is often the reason why we don't ask people to actually find inflection points, because it's just can be such heinous work. Yeah, does this factor? I don't think it does. So how do we solve this equal to 0? So what would you say? You're not wrong. You said take set each part equal to 0. Yeah. Now we know the bottom is going to be equal to 0 plus or minus root 6. The top part here, I'm going to go up here. So if I set x to the 4th minus 9x squared plus 12 equal to 0, it's kind of quadratic, right? It's like a u sub. So what I'm really going to do, instead of getting x equal to negative b plus or minus square root of whatever, I'm going to get x squared equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. I'm going to get x squared equal to 9 plus or minus the square root of 81 minus 48 is 33 all over 2. And so then x is equal to plus or minus the square root of 9 plus or minus the square root of 33 all over 2. I'm not kidding. I wasn't kidding. Really gross. Yeah, that's terrible. I don't love that at all. Some of those numbers are probably too big. It's not. Definitely not. So yeah. Ugh. 9 plus the square root of 33 is like 9 plus 6, which is like 15-ish. Divided by 2 is like 7 point something, which is bigger than the square root of 6. So definitely our actual critical points are x equal to plus or minus the square root of 9 minus the square root of 3 all over 2. Because 9 plus the square root of 33 all over 2 is too big. It's outside of the domain. So then that's where our inflection points would be. Terrible. So there's your 9 minus the square root of 33 over 2 in square root. And there's your 9, your negative square root of 9 minus root 33 all over 2. Comma, whatever the y value would be. Right? We don't want to find it though. It's terrible. And then, yeah, this problem is a good reason we didn't do this before. Or we didn't do for this one. This one's terrible. Terrible. No, no one's going to ask you to find the. So someone could totally reasonably ask you to graph this using the first derivative, but not to worry about any of the second derivative information. But no, here the second derivative is awful. Let's look at a better example. Better, different. The different example. Yeah. Let's look at this function. F of x equal to x squared divided by x minus 3. And we're going to do all the usual stuff. So, y-intercept. I'm not writing down the domain here. I'm definitely thinking in my head, oh, x equals 3 is not in the domain. I'm not going to write that down though, because unless I'm specifically asked to. So y-intercept, x equals 0, y equals f of 0, which is 0. X-intercept, set the whole thing equal to 0, which ends up just giving us x equal to 0. We do have a vertical asymptote at x equal to 3. We do not have a horizontal asymptote, but we do have a slant asymptote or an oblique asymptote, because the degree on top is exactly 1 larger than the degree on the bottom. So our slant asymptote we get via polynomial division. X times x gives me x squared. X times x is x squared. X times negative 3 is negative 3x. Subtract. 0 minus minus 3 is positive 3x. X goes into 3x 3 times. And you can actually stop there. You could also finish it. 3x minus 9. Subtract 9. So our slant asymptote is y equal to x plus 3. Cool. Then we start doing all the first derivative stuff. The first derivative, we're going to find f prime of x equal to the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, which ends up being 2x squared minus 6x minus x squared over x minus 3 squared, which ends up simplifying as x squared minus 6x over x minus 3 squared, or x times x minus 6 over x minus 3 squared. Our critical values are going to be x equal to 0, 6, and 3. And yeah, I would include 3. So again, I'm going to point out 3 is not a real critical value, but it is a place where the derivative is undefined. And I do care about including that on my sign chart for the first derivative. It's not a real critical value though, because the function is undefined in the first place. There isn't one.
Would it be worth it if do the limit as negative infinity and positive infinity just to see where the end behavior is?
No, not no, but no, because we don't need to, because well, just give me a minute and I'll expand on that. So looking at our critical values, our first derivative is looking like, so we've got 0, we've got 3, and we've got 6. And if I plug in something bigger than 6 to this factored form, it's going to be positive, positive, positive. If I plug in something between 3 and 6, positive, negative, positive. If I plug in something between 0 and 3, positive, negative squared is positive, so positive, negative is still negative. By the way, here's the thing I was saying. It's 6. 6 came from this factor with an odd power, the sign changed. 3 came from this factor with an even power, the sign stayed the same. 0 comes from this factor with an odd power, the sign's going to change. We can check it. You plug in negative 3, negative, negative, and the negative number squared is positive. So negative, negative, positive is positive. So take a look. That means our function is increasing, decreasing, decreasing, increasing. And this is why I think we don't really need to look at the end behavior, because we know that way off to the right, we're just going to get bigger and bigger and bigger and bigger and bigger. Way off to the left, we're going to get smaller, 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 smaller. Now, it could be like, you could also get something like this for a horizontal asymptote, right? You could have a horizontal asymptote that you're getting increasingly closer and closer to. But we already knew we didn't have a horizontal asymptote. So not having a horizontal asymptote combined with the function increasing to the right means we're probably going to increase off to infinity. And the function increasing on the left, meaning we're coming from a place that's low, means we're going towards negative infinity off to the left. We call that non-existent. That is one way we could not have a horizontal asymptote. But another example, just to point out, here is another function that doesn't have a horizontal asymptote. which doesn't go off to infinity in either direction. So I wouldn't say that generally is true. Yeah.
Like if I was on a test and they asked me for like critical points, do I include the point that's undefined or not?
It really, really depends on what they're asking. If they're specifically, if the question was specifically, what are the critical points of this function? The answer is 0 and 6. But if they're asking you to graph this function or do anything useful or define where the function is increasing or decreasing, we still need to definitely consider 3 as a point where things possibly change. So a couple things here. One, I would say we have a relative maximum at x equal to 0. We have a relative minimum at x equal to 6. And I would find the y value there. So I would say also that f of 6 is 36 over 3, which is 12. I'm going to graph it later. I don't usually ask these questions, but if we were asked where is this function increasing or decreasing, it is important to be very specific here. It is increasing on the interval negative infinity to 0 union 6, that's a 6, not a 0, to infinity, and it is decreasing on the interval 0 to 3 union 3 to 6. We cannot just say it's 0 to 6 because the function is undefined at 3.
Is there any reason we don't include 0 and 6 as functions?
Yeah, so I think we talked about this last time a little bit, but basically it is just a standard way of defining the intervals where a function is defined to be increasing or decreasing are typically defined as open intervals.
Okay, yeah, I remember that it's the convention.
So what? Yeah. So I'm getting like a million text messages here. Okay, never mind. Not important. So we can kind of see, right, we're already getting an idea of the shape of the graph. It's going to be increasing and then decreasing. So also this is nice because it tells me what's going to happen at this vertical asymptote here. Right? I'm going to decrease down to negative infinity, and then I'm going to come from positive infinity on this other side. It's kind of nice. I guess we should let's go ahead and find the second derivative stuff, even though I would normally probably just start graphing it at this point. So let's actually, I'm going to do part of the graphing just to kind of see what we've got here. So I know I've got a vertical asymptote at 3. I've got a slant asymptote at y equal to x plus 3. I've probably misjudged where I need to graph things. That's all right. And then over at 6, yeah, I've definitely planned poorly here. At 6, 12, I have a relative minimum. And at 0, 0, I have a relative maximum. So I have a pretty good idea of how this is going to look. It's going to come up like this. It's going to go down like this. It's going to come. Now I didn't give myself enough room up here. It's going to come like this, and then it's going to go like that. And there's my 6, 12. Sorry. You get closer and closer to my slant asymptote. But you can see how this function is obeying all the things we just said. Now, looking at this, we should be able to confidently say it's probably going to be concave down over here. It's probably going to be concave up over here. Well, let's find the second derivative. So my first derivative was x squared minus 6x over x minus 3 squared. My original function, just for completeness sake, was x squared over x minus 3. And my second derivative, okay, bottom times the derivative of the top, minus the top, times the derivative of the bottom, which is 2 times x minus 3, all over the bottom squared. Well, let's simplify that. So I can factor out an x minus 3 from the top. So I factor out an x minus 3. Can I factor out? Yeah, I can factor out actually 2 times x minus 3. Here's a 2 times x minus 3. Here's a 2 times x minus 3. I mean, I know there's one there too, but like, use that one. Why not? So I'm left with 2 times x minus 3 times x minus 3 squared minus x squared minus 6x. All over x minus 3 to the 4th. Cancel that one with one of those. Left with 2 times. That's going to be x squared minus 6x plus 9 minus x squared plus 6x. And look what happens. Everything cancels except for the 9. So left with 18 over x minus 3 cubed. So if we look at our second derivative, the only place where it's undefined is 3. If you pick a number larger than 3, like 4, this whole thing's positive, so it's concave up. Pick something less than 3, like 2, this whole thing's negative, so it's concave down. But we don't have an inflection point at 3 because it's undefined at 3. Even though the concavity changes there, we don't have an inflection point. I will also point out, just to back to your other thing, if you wanted to, you could say, oh, if we look back at our critical points of the first derivative, so I'll remind you here, our critical points were x equal to 0 and 6, and not really 3. If you plug in 0 to the second derivative, f double prime of 0 is 18 over negative 3 cubed, which is negative. I don't really care what the number is. But here's the thing to think about. We know, that at 0 you have either a max or a min, or maybe neither, because you can get neither. But if the second derivative is negative, that means the function is concave down at this potential max or min, or neither. If it's concave down, it's got to be a maximum, because the function's opening downward, and you got this point that's a critical point where the derivative is 0. Similarly, so if your second derivative, so if that's a critical point and your second derivative at it is negative, that means you have a relative max, which we already saw was true, right? Definitely relative maximum right there. Right there. In a similar way, hold on. In a similar way, f double prime of 6, 6 being a potential relative minimum or maximum or whatever. F double prime of 6, if you plug in 6 to this to the second derivative here, you're going to get 18 over positive 27, which is greater than 0, meaning it's concave up, and so it has to be a minimum at that critical point. Go ahead.
So if I understand correctly, the argument is if you have a graph that's concave down, and there's some point where the tangent equals 0, then it has to be the relative max because the concavity is downward.
Yep.
And similarly for upward, but you said the tangent has to exist. Isn't that the same thing as the derivative, the first derivative?
Well, that has more to do with being an inflection point than the second derivative test.
Okay.
So,
Here we don't have an inflection point because there's no tangent that makes it go straight.
right, but more importantly, because it's undefined there. So let's say a couple things here. So the second derivative test says the following. And we'll look at a couple easy. Oh my gosh, if I can move this paper here. So here's what the second derivative test says. So this is the second derivative test. And now what I want to remind everybody about is the second derivative test is not for inflection points. The second derivative test, that name specifically, is for relative extrema, meaning for maxes and mins. Here's what it says. If C is a critical value, meaning f prime of C is equal to 0, or f prime of C is undefined. Then one of three things can actually happen. If f double prime of C is positive, then C is a relative minimum. Because if the function is concave up and you have a horizontal tangent line, it has to be a minimum. Think about it this way, right? You're looking like this. There's your critical point.
How is that prime undefined? Isn't that vertical?
Well, we'll get there. So hold on. Or if f double prime of C is negative, then you have C being a relative maximum. Because the function is concave down, and oh yeah, relative max. And then thirdly, and this is the part that's a bummer, if f double prime of C is equal to 0, it's inconclusive. Meaning it could be a max, it could be a min, or it could be neither. We don't actually know without doing further inspection. And I'll give you some examples of how you can have all sorts of different things happen here. But first, let's go back to the other point. So here's an example of a function f of x equal to x to the 2/3, which definitely has a relative minimum at 0, 0. Right? The graph looks like this. And here, this second derivative test would be totally not helpful. If you take the first derivative, it's equal to 2/3 x to the negative 1/3, which is 2 over 3 x to the 1/3. And if we set that equal to 0, you get no solution. If we see where it does not exist, you get x equal to 0. So x equal to 0 is a critical value. Question?
If the second derivative test is
Mm-hmm.
why would you like that? When you can use the first derivative.
I agree with that statement. I wouldn't. The reason we are learning about this now is because it's the right place to learn about it, because it makes sense in context of graphing. And the reason we really care about the second derivative test is later on when you take 21C, there's a test for finding the extrema of a function of multiple variables. So instead of being like a function where your output's a line, it's like you have a surface. Like you have something that looks maybe like this. Some surface that's some sort of downward opening paraboloid. And the idea is to test whether this point here is a relative max or a relative min or something else called a saddle point. There isn't an analogous first derivative test, but there is an analogous second derivative test that allows you to use some second derivatives to tell whether this point here is a max and min or a saddle point. So that's why we're talking about this second derivative test now, is because so that it'll make sense later on when we talk about the second derivative test you need for this. That's really why. At least that's my opinion as to why. It also is not bad to use when you're doing optimization problems. Sometimes the second derivative test really is nicer than doing the first derivative test for optimization problems. So we'll point out here, if we take the second derivative. Sorry. So my second derivative here is equal to -2/9 x to the negative 4/3, which is -2 over 9 x to the 4/3. Oops, sorry. So I do have x equal to 0 again being a critical point for the second derivative. But the second derivative is undefined then. So I definitely couldn't use the second derivative test because f double prime of 0 is undefined. What's that? So some sign charts here for my first derivative, and I'm kind of getting this picture I drew is in the way. It's all right. So my first derivative, I can see that if I plug in something bigger than 0, it's going to be positive. Plug in something less than 0, it's going to be negative. We're decreasing, increasing. We definitely have a relative minimum at 0, 0, which we can also see from the graph. Certainly, the relative minimum at 0, 0. And then for the second derivative, if we do a sign chart, well, if we plug in something bigger than 0, like 1, the whole thing's negative. Plug in something smaller than 0, like -1, the whole thing's negative. So it's definitely concave down, which again, the graph agrees with. Question?
Yes, so I'm having a little bit of confusion with the definition of the second derivative test because from my understanding of what we did, and correct me if I'm wrong, if the first derivative does not exist, so if our critical point doesn't come from the first derivative being 0, then the second derivative can never be applied.
Right.
So why do we even include it in the definition? Why don't we just say if f prime of x is 0, then the second derivative?
Yeah, you might be right. I'm not sure. It might actually not be included there. Yeah, that might be. I might have this part might not actually be part of the.
I thought maybe there was some way that.
Yeah, I don't know. I'm not sure. I'll have to go look. But I think, yeah. Let's look at a couple more examples because it's definitely worth seeing. So let's say we had, sure, let's look at this one. So let's say our function f of x was equal to x cubed minus 4x squared. 4x squared? No, 6x squared. And I want to find my critical points. I want to find the relative extrema, and I want to talk about the different ways we can do it. So, relative extrema. I don't really want to graph this one. We've graphed it before. My first derivative is 3x squared minus 12x equal to 0. Factor out to 3x. And we get x equal to 0 and x equal to 4. We could use the first derivative test, but let's go ahead and use the second derivative test. So second derivative f prime of x is equal to, well, it's just 6x minus 12. If I plug in 0, f double prime of 0 is 0 minus 12, which is negative, meaning we have a relative maximum at x equal to 0. Similarly, f double prime of 4 is equal to 24 minus 12, which is positive, meaning we have a relative minimum at x equal to 4. It's totally fine. I just don't find this very informative in that it's not going to help. Like if I'm only trying to find relative extremes, sure, it tells me if the max or min, but it doesn't really tell me if it's going to be increasing, decreasing, right? Any of the other good information we would like to have from the first derivative test. Also, it doesn't always work. Let me show you what I mean. Let's say we had f of x equal to, this other good one, x to the 4th minus 4x cubed. So now if I take the first derivative, I get 4x cubed minus 12x squared equal to 0. I factor out a 4x squared with an x minus 3. So my critical values are x equal to 0 and x equal to 3. The second derivative, double prime of x, is equal to, let's see, 12x squared minus 24x. Or, as I would factor this out, 12x times x minus 2. If I plug in 3, it's helpful. F double prime of 3 is 36 times 1, which is positive. So we know we have a relative minimum at x equal to 3, because the function is concave up there. But at 0, f double prime of 0 is 0. And that means I don't know. It could literally be anything. It could be a minimum, it could be a maximum, or it could be an inflection point. So to tell what's happening at 0, you actually have to go back and then use the first derivative test. There is no other option. So I use the first derivative test here. 0 and 3. I pick a number larger than 3, like 4, positive, positive. Pick a number between 0 and 3, like 1, positive, negative. Pick a number less than 0, like -1, positive, negative. So my function is decreasing, decreasing, increasing. So I have a relative minimum of 3, and I don't have a relative extreme at 0. I would also point out, because I do think it's important to point out, I would say this function is increasing on the interval from 3 to infinity, and is decreasing on the interval from -infinity to 3. I include the 0 there because it's part of the domain of the function. It's probably going to be true that if I didn't have a relative extreme at 0, it's probably going to be an inflection point if the second derivative test was inconclusive. So we look at the second derivative number line, which has critical points 0 and 2. Pick a number larger than 2, like 3, positive, positive. Between 0 and 2, positive, negative. Less than 0, negative, negative. So it's definitely concave up, concave down, concave up. So I do have an inflection point at x equal to 0 and at x equal to 2. You get correct. You can only find whether or not you have an inflection point by finding where the second derivative is equal to 0, and then the concavity has to change there. Again, that's not the full definition, but it's mostly the definition.
So with the inflection point, if the second derivative goes from positive to negative or negative from positive, it is guaranteed that most of the
time, yes.
At least within
Unless you have some weird, so let me point out here, let me draw you a picture of something that's not an inflection point. Just to kind of clarify this. And this is where things get weird. So if I had a graph that looked like this, I'm just gonna make up something I'm not, so, well, in fact, I know what I can do. So let's say my graph was f of x equal to x squared when x is less than 0, and the square root of x when x is greater than or equal to 0. So here's my x squared, something like this. Definitely concave which way? Concave up. And here's my square root of x. Definitely concave which way? Concave down. So here's what I would say. Just looking at this without doing the work, just seeing what I see. I would point out that certainly f of x is decreasing from negative infinity to 0, and it's increasing from 0 to infinity. And certainly f prime of 0 does not exist. There's a couple ways you can argue this. We could use a limit definition if you really, really wanted to, but you can also point out that this function over here, the derivative is something certainly negative, negative, negative. Derivative over here is something positive, 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 and they're both not approaching the same value. Sure.
Is it better to use the limit definition for the first function? So we would say limit as f approaches on the right and f approaches on the left, or is it better to take the derivative of both?
So it's really the technically correct way is the first thing you're saying. So if I want to show that f prime of 0 does not exist, I would say, well, I know the limit definition of f prime of 0 is the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. But you want to be specific here, though. You want to make sure that you use the limit definition for the point of interest. You don't want to do f prime of x. You want to do f prime of 0. So then that's going to be the limit as h approaches 0 of f of h minus f of 0, which is 0, because f of 0 is the square root of 0. So I've got the limit as h approaches 0 of f of h over h, and then we have to split it up into the two-sided limits. You have to go from the left and the right. So if we go the limit as h approaches 0 from the left, well, then I'm less than 0. So then I'm using this piece of the function up here. That's going to be f of h is going to be h squared over h. And that's going to be the limit as h approaches 0 from the left of h over 1, which is just going to be 0. If I go from the right, well, then I'm bigger than 0, so I'm using the square root part. So f of h is going to be the square root of h over h, which simplifies to the limit as h goes to 0 from the right of 1 over the square root of h. And as h goes to 0, 1 over root h goes to infinity. Which we can see from the graph, right? Here, definitely the slopes of the tangent lines are getting closer and closer to being 0, which you can kind of see. Here, the slopes of the tangent lines are getting steeper and steeper and steeper, closer to infinity. So since the left and the right hand side of this limit don't match, the limit doesn't exist, and the limit is what the derivative is defined to be, so the derivative does not exist.
Our function is defined as x power of g over 2 for when it's greater than 0. Then we get 0, but it would be different 0 because one is positive, one is negative, right?
As long as they're both approaching 0, if they're both approaching 0, then it would be fine.
Even so, our first 0 right here is a negative 0, right? Because h is a slightly negative.
Are you saying what h is approaching or what the limit ends up being?
The limit ends up being
0 is 0. Nope. If you evaluate the limit, there is no slightly less, slightly bigger than. Once you have about this is not a positive or a negative 0. This is a 0. End of story.
So if the other function was h to the power of g over 2, there would be a derivative.
Probably, yeah. Let me think. H to the 3 over 2. I forget what that looks like, to be honest. But it would make sense. Yeah. Yeah. You're probably right. I mean, let's graph it. Let's see. I'm not as good at graphing h to the 3 over 2.
The reason I came up with that example is just
Yeah, that makes sense.
Is what I'm trying to understand. Because it averages 0, but it averages 0 from the positive end.
So if we do y equals x squared. When x is less than 0. Oops, x. And x to the 3/2. Come on. Yeah, I mean, so that's pretty plausible. Come on, geez. Yeah, it looks to me certainly like that derivative would exist there. Cool.
Okay, so the only time where we care about whether zero is approaching from the left or the right is with composite limits.
No, we care, it depends. But that's not an easy question to answer. We care lots of times, it just depends.
So it's important to know if we're approaching zero from the left or the right, even after we evaluate the limit.
I'm not sure what you're asking.
So for example, in this question, we are approaching zero from two different directions, right?
Right,
Here, the derivative still exists,
right.
but does it matter at all? Not in this question, but in other contexts, whether the derivative is approaching zero or number from the left or the right.
Well, so when h is approaching 0, it's approaching 0 from both sides. Sometimes we have to evaluate each side independently to determine if they're the same or not. Sometimes we don't. So back to the other question though, this function certainly does not have an inflection point at 0. Because even though the concavity changes, we can't have an inflection point here. Now, I'm going to say something that's not quite what you think I might say. I'm not going to say because the derivative doesn't exist here. I'm going to say because f of x does not have a tangent line at x equal to 0. And here's why we use this language specifically. Here's the example of a function that is kind of annoying. F of x equals x to the 1/3. Graph this function. Looks like this. It definitely looks like it has an inflection point there, right? The function is smooth. It looks pretty differentiable most of the time. It changes concavity from concave up to concave down. And it certainly has an inflection point at 0, 0, but it does not have a derivative there. So I'll point out f prime of x is equal to 1/3 x to the negative 2/3, which is 1/3 x to the 2/3, and has a critical point at x equal to 0 because f prime of 0 does not exist. This is also interesting. So on my number line for the first derivative, the derivative is positive on the right, positive on the left. So it's increasing, increasing. And so I would say this function is increasing on the interval. All right, let me ask you all. The interval, do I include the 0 or do I have to exclude the 0? I'm going to include the 0 because it's in the domain of the original function. Except I just wrote the wrong thing. There we go. Second derivative is equal to, let's see, -2/9 x to the negative 5/3, or if you prefer -2/9 x to the 5/3. Critical point for that second derivative is also 0. For like f double prime, the second derivative is negative over here. Plug in 1, positive over here. I plug in -1. So it's concave up, concave down. And we do have an inflection point at x equal to 0. Because even though the first derivative is undefined at 0, the function does have a vertical tangent line at that point. It's kind of an annoying distinction, but it's kind of the way people define it. So inflection points, typically, generally, it's just where the concavity changes and the function is defined. Technically, there's this little extra thing that you have to worry about where the derivative doesn't always have to exist, but mostly kind of has to exist. Basically, either the derivative has to exist, or if it doesn't exist, the slopes of the derivative on this side should be approaching the slopes of the derivative on that side. Kind of weird. Kind of a corner case. We shouldn't really worry too much about it. What are other questions about that before I move along? The other thing I wanted to point out, I know I kind of got off track here, is that so in this example we did back here, not that one, sorry, not you, you were terrible. In this example here, we saw an example of where the second derivative test was inconclusive, and our critical point that it was inconclusive for ended up being an inflection point. But it doesn't have to be. You could also have something like f of x equal to negative x to the fourth. First derivative is negative 4x cubed. Critical point is definitely x equal to 0. And if you use the second derivative test, f double prime of x is negative 12x squared. If you plug in f double prime of 0, you get 0. Could be a max, could be a min, could be an inflection point. Maybe none of those. We don't know unless we use the first derivative test. If you go back to the first derivative test, it's pretty clear. Plugging something bigger than 0, like 1, the whole thing's negative. Plugging something less than 0, like negative 1, the whole thing's positive. So the function's increasing, decreasing. So we definitely have a relative maximum at x equal to 0. So if you're using the second derivative test, that's totally fine. Just be aware that if you get 0, you have to do something else to test whether or not that thing is a max, a min, or something else. Cool. Let's look at some more examples. I got time. So let's say we want to graph f of x equal to x e to the x, including all of the usual things. So y-intercept, x equal to 0, y is going to be 0. X-intercept, set the whole thing equal to 0. Be careful. People, when they do this, they often like to set each factor equal to 0. So you get x equal to 0, great. Or you get e to the x equal to 0. Not great, because there's no solutions there. So just be aware that if you're setting e to the x equal to 0, you're never going to get a solution. E to the x is always positive. E to the anything is always positive. A positive number to anything is always positive. And then we would do asymptotes. Ooh, asymptotes, interesting. There won't be a vertical asymptote. There's no division by 0. There's no logarithms. But there could be a horizontal asymptote. And this is where things get tricky. So if I was going to do the horizontal asymptote, well, let's look at the limit as x goes to infinity. As x goes to infinity of x e to the x, I get infinity times infinity, which is infinity. No horizontal asymptote to the right. If I go to the left, I've got infinity or negative infinity times e to the negative infinity. E to the negative infinity is actually, well, think about the graph of e to the x. To the right, e to the x goes to infinity. To the left, e to the x goes to 0. And what's negative infinity times 0? Right. It's actually indeterminate. It's like 0 divided by 0 or infinity divided by infinity. In fact, I would encourage you all to think of this as the limit as x goes to minus infinity of x divided by e to the negative x, which is a negative infinity over infinity. Which one's bigger? So we actually do have some sort of inclination as to which of these functions is bigger. If you think about x versus e to the negative x, x is going to infinity. Yeah, I mean, right, not super fast. E to the x goes to infinity super fast, comparatively. So this is I might write this kind of a silly way. This is a negative infinity over infinity. This infinity is a bigger infinity. So this actually does go to 0. Now, shortly, next week, we'll talk about L'Hopital's rule, which is actually how you would determine that this limit was equal to 0. Now, the nice kind of thing about this is you can kind of get away without doing this if you look at all the other stuff that your graph has to tell you. So we're going to come back to this and say, like, we could have probably seen this without actually finding this, but then next week we'll talk about L'Hopital's rule. Let's do the first derivative stuff. F prime of x is going to be 1 times e to the x plus x times e to the x. I'm going to factor. Set that equal to 0. I'm going to get x equal to -1. I'm going to use the first derivative test because I'm not a fool. Because it's the best test in my opinion. And so if I pick a number bigger than -1, like 0, positive, positive. Pick a number less than -1, or I can just see the sign is going to change. So it's decreasing, increasing. So I have a relative minimum at x equal to -1, and y is going to be, if I plug in -1, -1 times e to the -1, or -1 over e. Second derivative stuff. So looking at my first derivative, I'm going to take the derivative of that. I would probably use this version. Take the second derivative of. I'm usually trying not to. I don't know. Either way, it's fine, I guess. Derivative e to the x is e to the x. Derivative x e to the x is what I just did. So I should just take the derivative of x e to the x to be all of this and write that out again. So it's going to be plus e to the x plus x e to the x. Factoring out e to the x, I get e to the x times 1 plus 1 plus x. So I'm going to get x equal to -2 as my critical value for the second derivative. Using my sign chart for the second derivative, I can see if I plug in a number bigger than 2 like 0, it's positive. Number less than -2, it's going to be negative. So it's concave down, concave up. So I definitely have an inflection point at x equal to -2. If I plug in -2, I get -2 times e to the -2, or -2 over e squared. So then I try and put it all together in a graph. So putting it all together, let's see here. Can we see here? So I've got a couple points. I've got the point 0, 0. I've got the points, where were they? -1, comma -1 over e, and -2, comma -2 over e squared. Before I plot these points, I'm going to think about the fact that my graph is going to be decreasing before I get to -1 and increasing afterwards. So it's going to be decreasing, increasing. I know that my only x-intercept is right there. I have an inflection point right there. So it's going to look something like this. Concave down, concave down, concave down, concave down, concave up, concave up, concave up, bottom out. Looks like that. And I can kind of know that I have to have a horizontal asymptote to the left because I'm right. The function is decreasing from left to right, but there's no x-axis. I can't cross the x-axis anymore because I don't have any x-intercepts. So I'm kind of stuck with this horizontal asymptote behavior. There's not really anything else that could happen. Something else to be aware of. Yeah, there's my inflection point at -2 over e squared. And there's my minimum at -1, comma -1 over e. Question?
So we can explain. One is basically concavity is how fast the first derivative is increasing or decreasing.
Right.
It's basically how fast is a function. Is a function increasing at an increasing rate, or is it
Right.
decreasing at a
So in fact, we said this before, and I think now is a good time to say it again. So if f is concave up, that's equivalent to the first derivative increasing, which is equivalent to the second derivative being positive. And similarly, if your function is concave down, a different color bad. If you're concave down, that means the first derivative is decreasing, which means the second derivative is negative. Now look at this graph for a second. Way over here to the left, the derivative is very, very, very slightly negative. I haven't drawn it maybe perfectly, but right, if you think about the tangent line there, it should have a very slightly negative slope. And then as we get closer and closer, the slope is a little more negative, a little more negative, a little more negative, a little more negative. And right here, it's as negative as it can be. and then it starts getting positive, positive, positive. So that's where we get our inflection point, where you have your derivative being either as negative as it can be or as positive as it can be. In other words, where the derivative has a maximum or a minimum, where the second derivative is zero. The derivative of the derivative is zero. Something else I wanted to mention here. Yeah, no, that's good.
So how about if the second derivative is zero? That's inconclusive. In terms of the graph being concave up and concave down.
Well, the second derivative is zero, which it is right there. That's where you have a potential inflection point, which we do.
But we can't say anything about the decreasing or increasing of the function at that point.
No, it's decreasing there.
Yeah, we know it's from the function, from the graph, but if we didn't have the graph, there would be if we just had one inflection point, so one point where we knew it was the inflection point, we don't have any information. Could we say the graph is decreasing?
If you only had an inflection point and didn't know anything else about the graph, no, you couldn't say anything about increasing or decreasing. But we did all this other stuff, right? We did the first derivative test. We know at -2, the function is definitely decreasing. There was something that keeps entering my brain and it keeps leaving that I wanted to say about this. Sorry, it's there. I just can't quite remember what it is. It was actually worthwhile. Brain, where'd you go? Sorry. There's something I want to say here that is, I feel like is important, but I guess it's not that important. Yeah, inflection points. Really, James. Like I keep coming back to it. Oh, I know what it was. There we go. So another way to think about what an inflection point on a graph is the point where the tangent line goes through the function. So typically, when you're thinking tangent lines, relative maximum, tangent lines above the graph. Relative minimum, tangent lines below the graph. Inflection point, I'm not going to draw this well, I promise you. I'll try my best. Tangent line goes through the graph. Well, you could say that's true, friend. That's always true. So the reason here basically is so this is an inflection point because this is where the slope is the most negative it can be, right? The slope of the tangent line is positive, less positive, 0, slightly negative. As negative as it gets, less negative, 0, positive, positive. So, right, this is where, right, this inflection point here is where the first derivative is, in this case, minimized. Or it could be maximized if it's going the other way. Yeah. Typically, I mean, unless you have some weird piecewise thing. But yeah, for regular-ish functions, that's it.
When we say truly graph, we just mean it intersects the graph.
Meaning on one side of the graph, the tangent line will be above the graph, and on the other side of the tangent line will be below the graph. With rare except unless your tangent line's vertical. Yeah, so that's why we say it goes through the graph because. Right. Okay, let's look at a couple more examples. What time is it? Yeah, let's just continue graphing. Graphing is good. Let's say we wanted to graph something like, what do I got in mind here? I had another one that's a typical example. Sure. Sorry, brain. Yeah, let's do this one. Let's say you have f of x equal to the natural log of x over x squared. All right, so first and foremost, domain. X has to be greater than 0. Which means our y-intercept is out the window, no y-intercept. X-intercept, we might have one. So we set the whole thing equal to 0, we're going to get the natural log of x equal to 0, which means x is going to be 1. It's natural log of 0. So we definitely have an x-intercept at 1, 0. Asymptotes. Asymptotes are interesting here. Let's talk about a horizontal asymptote first. We can't go to negative infinity because it's not in the domain. If we look at the limit as x goes to positive infinity of the natural log of x over x squared. So again, this is totally we would be able to do this with L'Hopital's rule, but for now we're just good. It also is good to have a sense about which functions are bigger than other functions. So let me ask you all, which function grows more rapidly? Y equals x squared or y equals natural log of x? X squared. But think about the graphs of them. X squared looks like this, whereas natural log of x looks like this. Right? X squared is way, 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 way bigger than natural log of x is. So we really have a tiny infinity over a much, much bigger infinity. I could prove what? Increases at a slower rate. Sure, but I guess by taking the second derivative.
Is that the basis for those?
No, it's not. Okay. But this limit is 0. Yeah. You could also pick, if you wanted to be a little bit more proofy, you could pick some values of x. Like if you pick x equal to 1,000, the natural log of 1,000, not very big. Like it's probably on the order of 5. I don't know. E to the 5th is probably bigger than 1,000. Maybe not. E to the 4th, maybe like 6. Whereas 1,000 squared is like 1,000,000. And 6 over 1,000,000, definitely very small. On the other hand, vertical asymptote, well, maybe 0. So typically you get a vertical asymptote when you have a non-zero number divided by 0. Whereas if you have a 0 over 0, that's where we typically have to do some sort of algebra to deal with the limit. So the question is, what's happening as x approaches 0 from the right of the natural log of x over x squared? Is this a 0 over 0 type of limit? Well, the bottom's definitely going to 0. What about the top? Yeah. And this is a slightly positive 0. So we actually don't have to do anything kind of bizarre here. You have a really, really, really negative number divided by a very, very small positive number. Big negative thing divided by small positive thing is a big negative thing. Think of this as negative 1 billion divided by 1. Well, I would say you're correct. It is undefined in a negative infinity sort of way. It is not indeterminate. So that actually brings up a good point. So just as a quick aside here, indeterminate forms, 0 divided by 0, infinity divided by infinity, infinity minus infinity, 0 times infinity, and there's a few others as well. But these are the ones we're seeing right now. But specifically, not indeterminate, infinity plus infinity, negative infinity minus infinity, infinity divided by a small positive number, or infinity divided by a small negative number. Those all work out just fine. Infinity plus infinity is infinity. Negative infinity minus infinity is negative infinity. Infinity divided by 0 is infinity. Infinity divided by a small negative number is negative infinity, right? We're just looking for signs here. So big number divided by small number is a big number. Big number plus a big number is a big number. In fact, I would encourage you when you're thinking about these infinity things to don't actually say infinity. Say big number. Because that's really what we kind of mean a lot of the time. This is a negative big number divided by a positive small number. Big number divided by a small number is a big number. the sign happens to be negative because it's a negative or a positive. That's what I think of when I'm doing this all the time. So this means we do have a vertical asymptote because as x gets closer and closer and closer to 0, the function goes down, 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 down. So great. We probably could have seen this without actually looking at that, but fine. I will point out, because the reason I'm actually kind of emphasizing this a bit is because it is important. We can when we talk about L'Hopital's rule next week, we can only ever use L'Hopital's rule if we have a very specific indeterminate form. If it's this one or this one. Any other indeterminate form, like this or like this, or like some other ones we'll see, like 1 to the infinity, or infinity to the 0, or 0 to the 0. All those have to be manipulated to look like one of these two forms before you can actually use L'Hopital's rule. It's fine. So we're going to graph this thing. So let's see here. We need to find the first derivative stuff. So my first derivative, f prime of x, is going to be, let's see, my function was the natural log of x over x squared. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. X squared over x is x, and I can factor out an x from each of these. So I'm going to have x times 1 minus 2 natural log of x, all over x to the 4th. You can cancel an x here and an x here. Oh, there was something I was going to say a while back that I meant to say. Just want to point out, as is typical with the quotient rule, if your denominator started with some power of something, your next denominator is going to be that same power, just 1 higher after you simplify. And that's what I wanted to point out in this example way back. Sorry. I do want to say this because I do think it's a pattern that's worth noticing. Look back real quick here. I had it. Nope, that's not it. I thought I had it. It's abandoned me now that I've looked for it. I guess not. Sorry, all over the place. I think I found, oh, there it is. I see it. It was in this example here, where our function was x squared over x minus 3. Our first derivative was x squared minus 6x over x minus 3 squared after we simplified it. And our second derivative was 18 over x minus 3 cubed after we simplified it. So every time you take a subsequent derivative of some sort of quotient, after you simplify and cancel out any kind of factors you can cancel, your new denominator should have the same base, but to a 1 higher power. Always true. It's kind of cool. It's kind of nice. It makes us have kind of a end in sight when we're trying to simplify a quotient. Okay. So back to this one. I set this equal to 0. Well, I'm not going to worry about x equal to 0 being a critical point because it's kind of the end of the domain. So it's going to end up on my number line anyway, but not as a critical point because it's not in the domain, but just as it's where we only have a vertical asymptote. I set the whole top part equal to 0. 1 minus 2 natural log of x equal to 0. 1 equal to 2 natural log of x. 1/2 equal to the natural log of x. E to the 1/2 equal to x. Number line 0, e to the 1/2. This is all garbage. And so I'm trying to figure out if my first derivative is positive or negative each of these. This is where we really do want to pick points. If I pick, say, e, which is bigger than e to the 1/2, natural log of e is 1. 1 minus 2 times 1 is -1. E to the 3rd is positive, so it's going to be negative in here. And here, if I pick e to the, I could pick e to the 1/4. I feel like I want to pick something else, but I guess no. I was thinking
Greater than 1 to the 1/2.
Well, right. That's what I was gonna say. Maybe I should just pick e to the 0, right?
Yeah.
Right.
Yeah.
Right. It's funny because I'm looking at these notes here, and they're like, someone picked e to the 1/4 as well. Like, why would you pick e to the 1/4? Like, you could do that, but I'm gonna pick e to the 0 because if I plug in e to the 0, natural log of e to the 0 is natural log of 1, which is 0, and 1 minus 0 is 1, and that's a positive. So we definitely have a relative maximum at e to the 1/2, comma, if I plug in e to the 1/2, I get the natural log of e to the 1/2, which is 1/2 over e to the 1/2 squared, which is just e. Or you might write that as e to the 1/2, comma, 1/2. All right, let's look at the second derivative stuff. Second derivative stuff, I believe, is fairly interesting here in a non-interesting sort of way. So look at my first derivative, which is 1 minus 2 natural log of x over x cubed. My second derivative is going to be bottom times the derivative of the top is -2 times 1 over x minus the top times the derivative of the bottom, which is 3x squared all over the bottom squared. So simplifying here, I've got x cubed over x and -2x squared. And then I've got, oof, this is kind of gnarly, minus a 3x squared times 1 minus 2 natural log of x over x to the 6th. I can factor out an x squared. I'm left with a -2 times a -3 times 1 minus 2 natural log of x. Cancel, cancel. Again, we're seeing that same thing happening, right? Where you end up with a 1 bigger power in the denominator. And simplifying the top, I've got -2 minus 3 plus 6 natural log of x. I feel like I've made an error here. Not really. It just feels like it's so funky. I want to double check. Nope, that's totally right. I was just hoping it was not, because it's kind of gross. So I end up getting -5 plus 6 natural log of x all over x to the 4th. Not the best thing I've ever seen. If we set that equal to 0, we're going to get 6 natural log of x minus 5 equal to 0, or natural log of x equal to 5/6, or x equal to e to the 5/6, which is just my favorite number ever. Number line again. That doesn't matter. So we look at our derivative here, our second derivative, which is this thing. By plugging in something bigger than e to the 5/6, like e, natural log of e is 1. -5 plus 6 is +1, so it's going to be positive here. By plugging in something smaller than e to the 5/6, like e to the 0. Natural log of 1 is 0, -5 over 1 is negative. So it is concave down, up, concave, whoosh, concave down, concave up. So we do have an inflection point at e to the 5/6, comma, this. If you plug in e to the 5/6 to your original function, which was natural log x over x squared, you get 5/6 over e to the 5/6 squared, which is e to the 5/3. Sorry. Graphically, here's what this looks like. We know that we have a vertical asymptote here. We have an x-intercept at 1. And it's been a while since we found it. And then we have a relative maximum at e to the 1/2 and a inflection point at e to the 5/6. So do something like this. Also, I should point out, we totally could have gotten away without even thinking about the horizontal asymptote at the beginning. Because if I know that my function is increasing up until I get to here and decreasing afterwards, and I don't have any other x-intercepts, I'm kind of stuck. I have to kind of get closer and closer to the x-axis. There really isn't another option. It's kind of cool. I kind of like that. All right. Questions?
I think about the odd and even thing that you said earlier, way earlier.
Sure.
So we know ln of x is obviously odd here because it's power 1, so the sign changes. That's why, isn't it?
I mean, what do you mean by the sign changes where?
So the factor e to the power of 5/6 came from ln of x, right?
Well, I would say it came from 6 natural log of x minus 5.
Right, which is odd here.
Right, because it's all raised to the first power.
Sure. So we know that it carries negative, and I've noticed before in a few other examples, The sign is pretty guaranteed to change if the factor comes from an odd factor. But here's my question, what if the factor comes from a function raised to some power that's the function itself? So if we have 2 to the power of x, would that be considered odd or even if the factor comes from like that?
Well, you're probably not getting critical values from that.
Because it doesn't equal 0.
Right.
Okay. Yeah, thank you, that's quick answer.
I mean, we could probably come up with something that was funky, but yeah. Let's look at, what time is it? Yeah, let's go ahead. So graphing is kind of a whole thing, right? There's lots of things to think about, but really it's intercepts, asymptotes, first derivative stuff, second derivative stuff. Use the first derivative sign chart to help you graph the thing. Because even though I didn't kind of explicitly say it, when I graphed this, I was really thinking about this sign chart for my first derivative and saying, oh yeah, look, my function is increasing up until I get to e to the 1/2 and then decreasing afterwards. All right. Well, let's talk about at least one optimization example because it is something you will also be learning about. So let's look at this one. Optimization is, it's a lot of interpreting words into math. I typically, in my head, group optimization and related rates together, even though they're not the same thing. They have a very similar process in that you're always having to take usually some amount of information given to you and actually figure out what the situation is before you can actually do the math part. So here is our optimization problem. We're going to make a trick-or-treat box. I know it's after Halloween. Late to the game. Oh, well. We're going to go trick-or-treating tomorrow. Thanksgiving trick-or-treating. You have 108 square inches of material to make an open-topped rectangular box with a square base. And when I say you have 108 square inches of material, what I really should be saying is we're going to make a box that doesn't have a top, and the most amount of surface area it can have is 108 square inches. So typically, when someone says the word material in the construction of a box or a cylinder or whatever, what they really mean is material is just a way of saying surface area. Typically. Without the top. What dimensions of this box will maximize the volume it can hold? So usually in an optimization problem, not always, but often, you will have some sort of thing you want to maximize or minimize, and then you'll have some other piece of constraining information. That's not always true. Sometimes they'll just give you the function they want you to maximize or minimize without having some constraint because it's already built in. But most of the time, there's usually something you want to maximize or minimize, and then some sort of constraint. And so I like to start by writing down, well, what do I want to maximize? Well, actually, first I like to start with a picture. Here's my box. I've not done very well. And I should pay attention. This is an open-top rectangular box with a square base, meaning this side of the box and this side of the box should have these same dimensions because it's a square base. Whereas the height of the box, I'll call y. So I want to maximize volume, which is equal to x times y. Notably, the thing you want to optimize typically should not ever be equal to a number, because we're trying to find out what the maximum volume is. We don't know it at the get-go. The reason I mention this is because often I've seen people say like, oh, x squared times y equals 108, because they see there's a number there and they want to like make it equal. It's not. The thing we want to maximize is just a function with variables and we don't know what it's equal to. On the other hand, our constraint is that the surface area should be up to 108 inches squared. I would say you could write it's less than or equal to, but really we should just say it's equal to, because we want to use up all the possible material we have, all of the surface area that we can use. You don't want to make a smaller box than you could, then you can make a bigger box. So we're going to say the surface area is going to equal 108 square inches. But we should really write an equation for that. So for this box that has 5 sides, all of the areas of the individual side should add up to 108. You've got your bottom side, which has an area of x squared, and each of the other 4 sides have an area of x times y. So I'm going to have 4 times x times y, and all that should add up to 108. There's our constraint. There's the thing we want to maximize. Typically, the thing we want to maximize or minimize is going to have too many variables. Because really, we know that if we want to maximize a function, we can maximize a function by taking its derivative, setting it equal to 0 to find the critical point, and then seeing if it's a max or a min based on the first derivative or the second derivative. But to be able to do any of that, we need our function to be a function of one variable. And this is the function of 2 variables. That's where the constraint comes into play. We're going to use the constraint to solve for one of those variables and then substitute that into the other thing. So we're going to isolate a variable in our constraint. Either choice is typically fine. You usually want to make the choice that is easier. Here it is definitely easier to solve for y instead of x. Solving for x would involve the quadratic formula, which we don't want to use. So solve for the one that's easier. So we're going to isolate y. So 4xy equals 108 minus x squared, and y is equal to 108 minus x squared divided by 4x. We're going to plug that into the thing we want to maximize. To thing we want to optimize. So plugging that in, now my volume equation is going to equal x squared times 108 minus x squared over 4x. And I think it's worthwhile to write this as v of x to really kind of be like, oh yeah, I'm finding the volume as a function now of just x. Before differentiating, it's probably in our interest to simplify this. I can cancel an x here and an x there. So I can write this as, I'm going to write this as 1/4 times x times 108 minus x squared, or really as 1/4 times 108x minus x cubed. Now we're going to find the critical points. I'm probably going to run out of room here. Maybe we're going to find the critical points. Yeah. So take the derivative, which is going to be 1/4 times 108 minus 3x squared. Set that equal to 0. So multiply both sides by 4. I could factor, but I'd rather just solve it. 108 equals 3x squared. X squared equals 108 divided by 3 is 36. Bless you. X is going to equal. Okay, so technically there's 2 answers to this equation. One of them is obviously not a sensible answer. -6 does not make sense for the length of a box. So even though x could equal 6 or -6, we're going to exclude answers that don't make any sense from a physical standpoint. It's totally true that, like, if you look at this function, -6 is in the domain of this function. 1/4 x times 108 minus x squared, right? -6 is a number you could plug in there, but it's not in the, what's the word we use for that? It's not in the implicit domain. Implicit. It's not in the explicit domain. So we would say explicitly, even though this function normally would be defined for every value of x anywhere, we're going to artificially, with purpose, restrict the domain to x being greater than 0, because it doesn't make sense to have a negative length.
Do you ever have a question like this where we have a coordinate system where the negative is important?
Possibly, yeah. It depends. But yeah, there's definitely, yes. I would say yes, generally. Yeah. So now here's where people differ on what to do next. After I find the critical point, usually I go back and this is a good time to read the question again. So let's go back and read the question again. You have 108 square inches of material to make an open top rectangular box with a square base. What dimensions of this box will maximize the volume it can hold? So we need to find all the dimensions. We found X, we need to find Y. So usually if you're trying to find the other dimension, you actually have that variable already solved for in the isolated constraint. Meaning we have already written right here that Y is equal to 108 minus X squared over 4X. So we should just go back to that and say, okay, Y equals 108 minus X squared over 4X. So if I plug in X equal to 6, I'm going to get Y equal to 108 minus 6 squared over 4 times 6, which is 72 over 24, which is 3. I should say X equals 6 inches and Y equals 3 inches. Now, there is one other thing to mention here, and that is that this question asked us to find the dimensions that will maximize the volume of this box. We found the only critical point, and we have assumed without actually showing it that it was actually giving us a maximum volume. But technically, we should check to make sure that this is actually giving us a maximum. There's a couple ways we could do this. One way to check, right? So we want to check, is X equal to 6 inches actually giving us a maximum volume? Well, one way we could check this is by using the second derivative test. We could say, well, V double prime is equal to, let's see, V prime, it was this, 1/4 times 108 minus 3x squared. So V double prime would be 1/4 times negative 6x. And if you plug in 6, V double prime of 6 is 1/4 times negative 36, which is negative 9, which is negative. So we're concave down, which means we have a maximum. So yeah, that works. Concave down means max. Or you can use the first derivative test and say, all right, well, now here's where we have to be a little extra careful, because for the first derivative test, our domain is restricted, right? We can't have X being negative, so we have to stop at 0. And we also have a limit as to how big X could be. Because if you think about having only 108 square inches of material, if X was the square root of 108, then the bottom would be 108 square inches, and that would take up all your surface area. So we have kind of a limited domain as well. So then my critical value being 6, I can see that the first derivative is going to be positive by plugging something like 1 and negative by plugging something like 7. And you can't see the first derivative. If you look back, if you plug in 1 there, it's definitely positive. If you plug in 7 there, it's definitely going to be negative. So it's definitely increasing, decreasing. So yeah, it's a maximum at X equals 6. Question?
Can you go with the reasoning of how you found the upper bound for the-
Sure. So we said that our constraint, we got to wrap things up here. So our constraint was that X squared plus 4XY was equal to 108. So we can see here that if I'm trying to think about how big X can be, well, first of all, let's say Y has to be positive or non-negative, right? Because if Y is negative, that doesn't really make sense. So if Y is positive, then the smallest and also X has to be positive as well, or non-negative. Okay, we're looking at this shape. So both of these are positive, then this number is, or I should say non-negative. Both of these are non-negative, and this number is also non-negative. So at the most, X squared plus 0 is 108. So that means X squared equal to 108 gives me x equal to the square root of 108. So the biggest x could be is the square root of 108, because let's say, for example, let's say x was 11. If x were 11, then no matter what y was, 11 squared plus 4 times 11 times whatever y is, that's going to be bigger than 108. And I don't have that much surface area to use. That's kind of the rationale there. Yeah. All right, I should stop talking. Mhm.
So this one was really easy in terms of thinking because the geometry is quite easy.
Sure.
It's a rectangle and then square.
Right.
But do we ever need to take this to something like a sphere or like half a sphere?
Or a cylinder. Yep,
Yeah.
for sure. Yes.
How does the reasoning work there?
The reasoning for what?
Any of those, any shape that's more complicated.
The same sort of way we did here. It's just it's the arithmetic and the algebra is a little more complex, but not so much more that it's not doable.
So here we knew that the surface area, we found the formula for the surface area for the reason that if we don't have one side, we can just times the bottom times the height, just not get that one side. Times all the sides, that's what I mean.
Right. We add right for a shape like this, we added up all the areas of the sides.
So what if it's something that's more complicated? Would we still, do we still have